Have you ever actually stopped to think about how a simple tap on your screen can cross an entire city, or honestly, even an ocean, in just milliseconds? We usually just chalk it all up to the invisible magic of Wi Fi, but there's an actual, deeply fascinating physical reality to the internet right beneath our feet. A reality that literally requires moving information through solid matter and open space. Welcome to The Explainer. Today, we're going to treat network engineering like a master craftsman's toolkit. We'll be exploring the physical blueprint of our entire digital world, tracking the amazing journey of our data as it transforms to overcome the very limits of the physical world. Here's our roadmap for today. First, we'll look at the wired versus wireless divide. Then, manipulating electrons, followed by harnessing photons. Next, navigating space. And we'll wrap it up with the ultimate connection ecosystem to see how all these tools manipulate physics to keep us connected. Let's get right to it. Section 1, the wired versus wireless divide. Before we get into the microscopic details, we really need to understand the fundamental split in how we actually transmit data globally. There is a remarkably strict boundary separating solid matter and thin air in networking. On one side, wired connections are all about absolute control. We rely on manipulating physical materials like conductive copper and highly pure glass, mostly to reduce signal loss over long distances. But on the flip side, wireless transmission leverages open space. It trades the stability of a physical cable for the ultimate freedom and mobility of the user. Moving on to Section 2, manipulating electrons. Let's explore the solid matter side first, looking at copper wires, our oldest but arguably most reliable networking tool. Now, pushing electricity through a wire sounds super simple, right? Well, it has a massive vulnerability. The absolute biggest enemy of any copper wire is electromagnetic interference, or EMI. Think of EMI as an invisible disruption caused by outside magnetic fields, things like power lines or heavy machinery. In a network, EMI acts exactly like loud, annoying static noise, interrupting a quiet conversation. It totally ruins the signal and causes data loss. So, how do we defeat EMI? Well, engineers leverage physics using twisted pairs. By physically twisting the copper wires tightly together, it creates opposing magnetic fields that literally cancel each other out. It works exactly like your favorite pair of noise-canceling headphones. We've got unshielded twisted pair, which is super common and cost-effective, and then shielded twisted pair, which wraps those twists in a metallic shield for heavily disrupted industrial areas. Because we're constantly demanding faster internet, engineers really had to push this simple twist to its absolute limits. They evolved these cables with tighter, way more precise twists and better materials to handle higher bandwidth frequencies. Think about the massive gigabit jump we've experienced over the years. We leaped from older Cat3 cables at just 16 megahertz up to Cat5e at 100 megahertz, and then blasted right past 250 megahertz with Cat6 to give us true high-speed internet. But what happens when twisting simply isn't enough? That's when we bring in coaxial cables. Coaxial tackles EMI using a completely different physical setup. It uses a heavy-duty metallic mesh shield that wraps all the way around the central data conductor. That thick mesh acts exactly like an armored Faraday cage. It's basically an impenetrable barrier that absorbs and blocks out external interference entirely before it can even touch your data. Section 3, harnessing photons. Copper is amazing, but electrical resistance eventually causes the signal to fade over long distances. So we needed a major upgrade. Enter fiber optics. When we swap out copper for glass and electrons for light particles, we are literally giving our network superpowers. Because they use photons, they are 100% immune to electromagnetic interference, zero static. Plus, they offer absolute data security because light doesn't leak signals that can be tapped into. They're incredibly lightweight, pack extreme bandwidth, and have unbelievably low attenuation, which means the signal can travel vast distances without fading away. But not all glass is created equal. When designing a network, engineers have to choose between two very distinct types of fiber. On one hand, you have single-mode fiber. This uses a tiny core to shoot a single laser straight down the center, perfect for massive distances. On the other hand, there's multi-mode fiber, which uses a larger core where scattered light paths essentially bounce down the cable. This makes it perfect for shorter, much more cost-effective runs inside a building. A microscopic cross-section reveals exactly why these two differ so drastically. It's all about the core sizes. Single mode has a microscopic core diameter of just 5 to 10 micrometers. I mean, it is razor thin.
Multimode, meanwhile, is much thicker, usually around 50 to 100 micrometers. It acts a lot more like a wide, mirrored tunnel that can handle multiple beams of light at once.
Inside those cores, physics really takes over. The wider core of multimode allows light waves to actually bounce along the edges at an angle. Now, this is awesome and super affordable for local networks, but it causes the signal waveforms to eventually blur and overlap if you try to send them too far. Compare that to the razor-sharp precision of single mode, where the straight, perfectly focused laser keeps the data incredibly crisp. That's exactly how we're able to run fiber lines across entire ocean floors.
Section 4. Navigating space. Cables, whether they're carrying lightning-fast photons or reliable electrons, literally tether us to a wall. To get true mobility, we have to manipulate invisible waves. Wireless transmission completely breaks that physical tether by shooting electromagnetic waves directly through the air. But it's not a straight shot. We have to cleverly interact with the Earth's physical geometry to bypass obstacles. We can actually bounce sky waves off the ionosphere, shoot line-of-sight waves straight from tower to tower, or even curve ground waves right along the Earth's crust. Ground waves, for instance, are absolutely fascinating because they operate at lower frequencies. They have incredibly long physical wavelengths. This literally allows them to hug the Earth's surface, effortlessly passing right through mountains and obstacles that would completely block shorter waves. This provides vital communication coverage for up to 150 kilometers. It's pretty amazing when you think about it.
Section 5. The ultimate connection ecosystem. So we've got electrons moving through copper, photons firing through glass, and waves curving through space. Let's tie the whole shebang together.
When you look at all these different mediums side by side, a really vital reality in network architecture becomes obvious. Every single medium has a trade-off between cost, distance, and interference resistance, which means there is literally no such thing as a perfect cable. Single-mode fiber totally dominates distance, but yeah, it's expensive. UTP copper is incredibly cost-effective, but it's highly susceptible to interference. You really just have to pick the right tool for the job. Imagine how these trade-offs build a modern city block. It's a totally elegant handoff. The massive data load enters the city via a single-mode fiber backbone. That fiber then hands the data off to heavily armored coaxial cables to run down your street. Then that coax hands it off to Cat6 twisted pair copper to safely bring it into your living room wall. And finally, your router translates those electrons into wireless Wi-Fi waves, handing the data off directly to your phone. It's a beautifully choreographed sequence.
So here's the absolute crucial point to take away from all this. Network engineering is never about searching for some mythical, invincible cable. It's really about masterfully assembling these disparate physical tools into a perfect working blueprint. It's entirely based on the specific limitations, budget, and physical environment you're dealing with. It is, quite literally, an intricate physical relay race.
So the next time you effortlessly tap a link on your smartphone, I challenge you to imagine that incredible relay race of electrons, photons, and invisible waves happening right beneath your feet. Just think about it, navigating miles of glass, copper, and thin air, all in milliseconds, just to bring you a single web page. Thanks for joining me on this explainer. Keep your curiosity sharp, and I'll catch you next time.